Thank you for joining us today. My name is Jacob Iden.
My name is Jessica Chung.
My name is Austin Moreno.
My name is Ricardo Mambrilla.
My name is Taylor Moyles.
And together we are Sound Engineering and Construction Management Group. Today we will be discussing our most recent project, the Montlake Lid Bridge project. For this presentation, we will begin by providing a brief background, detailing the conditions which govern this project. We will then outline the design process, which resulted in our final design. We will review the constructability of that design and give our final conclusion. The project is located in the northern scale neighborhood of Montlake. The neighborhood is currently separated by the Washington State Route 520. In order to reconnect the local community, it has been determined that a precast pre-stressed lid bridge be constructed to support a green space over sections of the existing SR 520, both east and westbound. This multi-span lid will extend approximately 780 feet and will be subjected to soil loads up to 6 feet, as well as trees, vegetation, and even a future light rail system. To support the loading described, a substructure comprised of 3 pier walls supported on a spread footing was implemented. And diaphragms support the girders at the ends as well as the top of the pier walls where the spans meet. The pier wall implements a hinge key connection, allowing rotation at the end of the spans. This is accomplished by extending a vertical steel dowel from the girders into the pier walls and into the end diaphragms so that the end condition of the span behaves like a pin connection.
So for our superstructure, we are working with the California wide flange girder. Since we're dealing with unusually high loading cases with the weight of the soil and HL93 loads, the wide flange shape is arguably the most efficient cross-section since the flange width can support a wider structure and distribute the load over a wide area. The wide and thick bottom accommodates more strands as well, and the wide flange shape also has greater stability in construction since it has a lower center of gravity and a greater plane of stiffness. Also, as opposed to using a bathtub girder, it weighs less as well, making it a bit more economic. When precasters invest in the forms, the wide flange shape becomes a very economic choice given the wide range of depths available. Combined with the use of high-strength concrete, the spans and girder spacings can be increased over the spacings for both T's and I sections. Despite these advantages, however, the wide flange girders comes with its disadvantages, specifically when it comes to deck removal, as it is more susceptible to damage. However, this can be done with cutting or jackhammering. The depth of 66 inches was determined through an iterative process in our calculations. Using that same method, we've determined that it required F'(C) of the slab and haunch to be 4 KSI, an F'(CI) of 5.5 KSI, and an F'(C) of 7.5 KSI at service. And you can see the cross-section of our wide flange girder to the right there. We have a haunch height of 2.5 inches and a deck thickness of 8 inches, as well as a girder spacing of about 8 feet. We made the girders a little bit closer as opposed to deeper for economic reasons, following the recommended girder spacings in the bridge design manual. There you can see the span lengths for girders 28 to 33 that we were assigned, which span from about 67 to 97 feet.
The gravity load path begins with the load applied to the deck, which is transferred to the girders, through the diaphragms, into the pier wall, and finally through the spread footing foundation. The vertical dowels, which establish the pin connection in the pier wall, are designed to carry the overstrength demands due to seismic loading. The pier walls were designed for shear and bending forces near the base, where it is fixed to the large spread footing, which are analyzed for both overturning and lateral sliding throughout the design phase. The overstrength demands are obtained by applying an amplification to the loading. This is to prevent plastic hinging, as the substructure is a capacity protective member. Additionally, seismic continuity was achieved by extending strands into the diaphragm. The image in the bottom right is a great example. This was a field trip that the class took to Confab, and you can see right here they extend the strands through the end of the girder, and that is for seismic continuity. Based on what I've told you, you're probably asking yourself, how did a group of 5 students design this entire project and come up with the construction sequences in just 17 weeks? Well, we had some help. In collaboration with our mentors, our scope was adjusted to design a segment of the multi-span structure in accordance to AASHTO LRFD 6th edition with Caltrans amendments. To manage the workload, the mentors made the suggestion that we focus on a 48-foot section and analyze 2 loading cases. The loading due to a 2-foot layer of soil and HL93 design load ended up controlling. For strength 1, service 1, and service 3, the HL93 combined with the dead load weight of the soil layer provides unusually high loading. Because we designed our section using Caltrans amendments for strength 2, we analyzed the P15 permit load combined with the 2-foot soil layer as well. When selecting the optimal cross section for the section analyzed, we began by designing a spreadsheet that allowed us to complete multiple iterations. Ultimately, we settled on the California 66 wide flange girder. You'll see on this slide the final depth span ratio was 0.065, which we realize is considerably higher than the typical ratio of 0.04 for a continuous span wide flange girders. However, due to the significantly higher load case, we believe it was an appropriate selection.
The creation of our superstructure followed an iterative design process in which we started by creating a girder design spreadsheet, following examples 9.1a and 9.1b of the PCI Bridge Design Manual. By doing this, we had a sanity check in that we could make sure all of our values are reasonable compared to the example. And as we were creating our spreadsheet, we were simultaneously creating our PG Super model. To ensure the PG Super model was acting the same way as our spreadsheet was, we added 3 exterior girders on either side of the 6 girders we were designing for both spans, as the PG Super manual explains that the 3 outermost girders are treated as exterior girders in analysis. Additionally, the HL93 and P15 live load moments were taken from PG Super and used in our spreadsheet to ensure that all values of the spreadsheet were being calculated off of known values, known correct values. The service 1 stresses under permanent loads were 1.04% different between our hand calculated values and the PG Super model. And the service 1 stresses under permanent loads and transient loads 1.24% different when compared to the PG Super model, indicating that our values were very close, as many of them were. We also ensured that the continuity assumptions being made by PG Super match the continuity assumptions of our spreadsheet by ensuring that the structural analysis method of PG Super was simple spans made continuous. As you can see underlined in red, the girders are treated as simple spans until they are made continuous. And we made that until after the deck placement, as you can see by the boundary condition. So once the deck is placed, the superstructure acts continuously. And we did this because, as you can see, the cast in place deck topping essentially ties the precast deck panels and girders together to create a continuous superstructure. Our spreadsheet indicated that 34 strands were necessary. However, if all 34 strands were straight, we experienced a failure at transfer in both our spreadsheet and in PG Super. To mitigate this, we decreased our eccentricity by raising the 4 strands. We harped the 4 strands, and this raised the center of gravity of our steel. And as you can see in the bottom right-hand corner, the girder design dashboard, as well as our hand calculated values in the spreadsheet, indicated that we were no longer experiencing a failure at transfer. For strength 1 and strength 2 considerations, we first found the flexural resistance of our members, which was very close. A ratio of 0.99 indicated that our hand calculated values were slightly more conservative, but they were almost exact. The strength 1 demand had a ratio of 0.89 between the PG Super and the hand calculated values, indicating that our hand calculated values, again, are more conservative. And we had a similarly close ratio for strength 2. As you can see in the bottom left-hand corner with the moment diagram, our demand is less than the capacity for both positive and negative moment. The negative moment was provided with number 9 longitudinal bars spaced at 12 inches on center. And as you can see on the right there on the girder design dashboard and in our hand calculated values, the strength 1 and strength 2 demands were satisfied. For shear design, the shear reinforcement was consistent across all girders, which is the case for all reinforcement, and all reinforcement was designed for our worst case girder, being our longest girder at 98 feet and 7 inches. As you can see, the minimum reinforcement was spaced, they were number 4s at 12 inches. Our critical section reinforcement were number 4 bars at 4 inches, or number 4 bars at 6 inches, and our anchorage zone reinforcement were number 5 bars at 4 inches. However, when we were doing this, we noticed that the demand was exceeding the capacity in the shear diagram. The demand was coming out of the envelope, essentially. So with a ratio of 1.08, this shouldn't have happened, and it could have been a PT supervisual glitch, but just to be conservative, or as Professor Matsumoto says, to sleep at night, we decided to be conservative and add number 4s at 3 inches, going 6 feet in from the face of both sides of the girder. As our critical shear occurs 5.83 feet in from the face of both sides of the girder, this just gives additional conservative shear reinforcement. With a ratio of 1.05 and 1.07 for strength 1 and strength 2 respectively, the demands we calculated are very close to the demands calculated by PG Super.
Appreciate that look at design RCE counterparts. All three of them did a tremendous job in efficiently designing this project. Put myself and Ricardo in a great position to not only manage, but execute the work. So our overview for today, we'll be diving into our pre-planning and site logistics. We'll begin talking about our project staging and girder specifics. We'll also take a look at our schedule and cost estimate. We'll take a look at risk and opportunity, and then we'll wrap up with our constructability review. So looking at pre-planning and site logistics, our governing agencies for the project were the Washington State Department of Transportation and the AASHTO Bridge Design with Caltrans amendments. Both agencies and jurisdictions were completely comfortable working in, being on past projects before and having a good understanding of what's expected. Looking at permitting and environmental compliance, we'll be having encroachments on both the north and south side of the project from city right-of-ways. And then looking at ESA and sweepy are also important on this job with surrounding wetlands, native species, and making sure that we're on top of that is going to be very important. As far as traffic and pedestrian impacts, it is a major expressway. Close to 90,000 cars are commuting back and forth from the I-5 and 405. And then, adding on to that, there's going to be a complex off and on-ramp system. And then we'll also, needed to think about girder and panel procurement. So, finding a good fabricator that was local, and looking at crane selection and trucking as well. We broke up the project into 3 stages. Our first stage consists of site prep, striping realignment, our initial demo of our carpool bus lanes on both directions, and then our median pier wall construction. Stage 2 dives into continued demo, major road and ramp realignment, and then construction of our outside pier walls. And then in stage 3, we wrap up with our girder erection and our slab placement. For being a congested highway, we're pretty fortunate to have a pretty decent amount of access to construction staging for our equipment and materials. This is a huge advantage because we're not having to have a lot of transport in and out of materials on a daily basis. We have access to storing equipment and, like I said, materials on both the north and south side. Just making sure everything's staged on the proper side of the freeway. That way, we're not struggling to track things on the off ramps and get them over on the bypasses. It's just we just need to be as efficient as possible with that. So looking at demolition on stage 1, like I said before, we'll be taking out those bus carpool lanes on both sides, and then also starting to work on the existing concrete barrier in the middle. We also need to, like I said before, we'll be moving our striping as far away as possible from that median wall. That's going to maximize the amount of space that we have, not only for safety, but just feasibility in itself. And then in stage 2 demo, a little bit more on the north side, and then mostly on that south side where that eastbound on-ramp is currently hugging the Pier 3 wall. We'll be kicking it out in the next slide. You'll get a good visual of that. That's going to allow for our work on that Pier 3 wall. So like I mentioned before, we'll be kicking out that eastbound off-ramp colored in blue there. That's going to open up a lot of space on that south side. And then we'll also be shifting both the east and westbound lanes as close to the wall as possible. That wall is now completed. And this is actually, we're going to be the permanent roadway will be for final construction. For our pier wall, we decided to go with a metal ply form system. This is a system that our company is super familiar with. We do own all of our material for this type of setup. It's pretty efficient, especially with our varying heights of our pier wall being stepped. It allows for quick adjustments to various heights and not only erecting the formwork but stripping as well. I'm going to hand it off to Ricardo, and he's going to continue.
For our CIP panel and girder fabrication facility, we chose Lafarge Holcim. We chose this facility because of its location and its route accessibility to the job site. Our crane staging, as depicted here in the pictures, the cranes will be placed on SR 520. The trucks will be coming in from the westbound, and we will be erecting in the yellow picks 1 through 6 and 7 through 12 in the green. We'll talk a little bit more about the girder erection sequencing in the next couple slides. Precast girder setup. So our heaviest girder at 99,000 pounds. Our pick points for the 67-foot girders are 5 feet from the outer edge of the girder. And then our pick points for the 94 to 98-foot girders are 8 foot from the outer edge of the girder. We chose a 350-ton hydraulic crane. From our load charge, that's what we calculated was needed. Two main factors in determining crane size are the horizontal distance of the pick and the weight of the girder itself. The precast girder erection sequencing. So on the westbound lane, we have picks 1 through 6, which are our 67-foot span girders, and picks 7 through 12, which are our 94 to 98-foot span girders on the eastbound lane. Our construction schedule, we have 3 stages of construction. After our notice to proceed, we could start to mobilize and submit our shop plans. Once our shop plans are completed, we can start the girder fabrication and CIP panel fabrication. In the meanwhile that's being done, we can do our site prep, demolition of our carpool bypass, and CIP panel striping, realignment, and construction of median pier. In our second stage of construction, we have a continued demolition, road and ramp realignment, construction of outside pier walls. And in our third stage, after that's been done, we have our girder erection, CIP panel placement, rebar installation after that. We pour our deck slab, and then we do our punch list closeout and demobilize. Our cost estimate, we came to a total of 8.9 million for the scope of work that we were assigned, with a job overhead of about 915,000, with a 2% bond, which is 180,000, mobilization cost of 890,000, which puts us close to 11 million. After including sales tax and the markup, a total of 12.9 million for the project cost, for the project bid. Risks and opportunities. We have a congested highway, so we need to be wary of traffic at all times. Multiple project stages, so we need to be wary of letting the civilians know of changing site conditions. Complex lid structure, limited day working time, so most of the work time is going to be during the night. We need to be wary of the environmental impact we cause by our construction. Some of the opportunities are that we get access to full closure of SR 520, which gives us manageable crane access, girder transportation, night work tolerance, and we have another opportunity is a partial precast deck panel design for our slab pouring. For the constructability review, we have our lid precast panel system and our precast girder advantage. For the girders, the advantage of the girders is that there's no false work required. There's short closure times of the freeway, less on-site construction and more construction on the prefab side. For the formwork for our slab, we decided to consult the CE counterparts for that. And we decided to go with a lid precast panel system, which Jessica will be talking a little bit more about in the next slide.
Right, so for the partial depth precast deck panel design, we followed the Caltrans precast deck panel user guidelines to determine a required precast deck panel thickness of 3.75 inches. Pre-stressing steel strands in our precast deck panels will be 3/8 inch diameter, grade 270 low relaxation strands placed at the centroid of the deck panel cross section to ensure that pre-stressing does not have any eccentricity. That attached picture is from the confab tour. It's a precast deck panel stressed in 2 directions at 0.7 ultimate strength to prevent splitting of the panel at the ends. The precast deck panel will be pre-stressed in the direction of the panel design span and perpendicular to the longitudinal axis of the girders. The pre-stressing strands in our precast deck panels will be extended about 4 inches in the cast-in-place concrete portion of our slabs, and the upper surface of the deck panels will have a 1/18 inch roughened finish to ensure composite action with the cast-in-place concrete. We were also able to determine a cast-in-place topping thickness of 4.25 inches. Our panel lengths would be at a maximum length of 9 feet, and since we have a 4-foot gap between the edges of each girder, we determined a necessary panel width of 4 feet and 2 inches. Getting to these values was actually quite simple since the Caltrans precast deck panel user guidelines laid out its instructions and requirements in a really intuitive manner. Surprisingly, this is not common in California, even though the precast deck panels provide an immediate platform and eliminate any need for formwork. So in conclusion, I think this project gave us great perspectives about working in industry. It's a little chaotic and riddled with work, but I think I can speak for everyone here that we gained some really valuable information throughout the semester when it comes to precast and pre-stressed concrete. We were really humbled by the amount of dedication that the mentors, Professor Matsumoto and Professor Anderson, had invested in our teams, let alone the project itself. The CE and CM collaboration was certainly a challenge, but the experience gave us great exposure to what it's like when a project requires the integration of construction management and civil engineering. And so with that, we say thank you and open up to our Q&A.